Hi, everyone. Here we are in the class. So far, we've mostly been doing basic setup for kinds of figure quantification for the kinds of conventions. So, what have we done? We've defined very basic marginal things like marginal mean consistency, which just means that your model is done by marginal quantile consistency, which is just the analog to quantile. And we thought of these as sort of sanity check conditions, which that good models will pass, but really bad models will fail. But the relevant thing about these conditions were that to the extent that we have a model that fails one of these sanity checks, that fails one of these consistency checks, we had very simple, concrete ways to fix them in ways that improve them. A concrete way we instantiated that was sort of notice that you correct the class, you could prove that squared error is related to the fact that squared error was proper scoring rule or like that's how you look at means. And similarly, there was a function called pinball law that if you improve your prediction with respect to marginal quantile consistency, you improve on pinball. And we also saw some basic tools to take these kinds of mean and quantile conditions that we might be able to establish in samples on like data we've drawn from some distribution and lift those guarantees over to the distribution which they were drawn, so we can generalize from data. And then last class, one of the things we did is we sort of revisited the setting that I had sort of introduced very briefly at the very beginning of sequential prediction, where there is no distribution, and I just make predictions as I go. And sort of saw there was a really not very compelling algorithm that would make unbiased prediction, okay, that would sort of satisfy marginal mean on the transcript. The algorithm would just predict every day that the thing that's going to happen today, the outcome today is going to be whatever the outcome is. Okay, so this is not like a super compelling algorithm, and maybe we're sort of towards this idea that we really want something stronger than marginal guarantee. What I want to do today is show you how to get marginal quantile consistency in the online setting using a slightly less silly algorithm. This is one that you might actually use. We'll talk about that a little bit. And then get to sort of our first actual application of these things, which is conformal prediction. So in general, especially the way I've been speaking thus far in this class, I've sort of been poo-pooing these marginal guarantees, saying, oh, these are really silly. These are sort of the level 0 kind of consistency conditions that you might want to ask for, and but eventually we're going to want to ask for more. All of that's true, and we're going to ask for more, but conformal prediction is a driving field in uncertainty quantification that's essentially based on just marginal quantile guarantees, and it's not it's like it can be useful, and its strength is in its generality and simplicity. So we'll give sort of the basic version of conformal prediction, which covers 90% of what the research literature in this area does. And then this will be one of the this will be like an application of marginal guarantees, and one of the things that we'll aim to strengthen as we develop in this class techniques we're talking about conditional guarantees. Okay. That's a bit just a reminder of what we've done like so far. But does that make sense? Are there other questions about that stuff before I go on? Cool. Okay, we wrote the definition down last time, but let me sort of remind you of what I mean by marginal quantile consistency in the online sequential prediction setting, where there is no distribution. Then we'll see how to repeat it. online sequential setting. The current distribution. What we do today, we observe features, potentially make a prediction, and we observe what the label was. We say that the prediction of the label for real values right now. Okay, and that accumulates over T rounds into a transcript, and the thing we care about when we talk about guarantees in online settings are properties of that transcript. And we're interested in algorithms that, no matter what the sequence of examples and labels are, will always generate transcripts that have nice properties. And one of the nice properties is what we call marginal quantile. What does it mean? Well, remember, you think about the model as tempting to predict every day, given the features xt, what, say, the 90th percentile quantile is of the label distribution. Okay. Now, suppose that we're succeeding in doing it. Well, in that case, we just counted the fraction of the days for which the label was smaller than the prediction. Compared that to say 90%, or more generally Q, where Q is our target quantile. Quantile consistency with respect from quantile Q. Then if we ran this thing for long enough, be zero. Right? We were correct, and we were predicting the 90th percentile quantile of the label distribution. We should our prediction to exceed the label. We'll say that our marginal quantile consistency error is alpha if it doesn't equal Q, but if it deviates from Q in one direction or the other by alpha. Yeah. Okay. So remember, like, if you're going to give algorithms that guarantee this property, in the worst case, over what the sequence of examples is, they can't exactly depend on like trying to learn like the correct distributional quantile from data and then predicting that, because there is no distribution, there are no correct distributional quantities. They've got to be adaptive in some way. You've got to have worst case guarantees. And let me show you a very, very simple algorithm for doing this that is a little bit less silly than the algorithm we saw last class for having a statistical bias which is predicted every day over time. Let's call this online marginal quantile. And it takes two arguments. What the target quantile is Q and some learning rate data. So it's going to update its prediction every day as a function of the confidence prediction of day 4 and whether it succeeded, whether the prediction actually exceeded the target, or whether it actually exceeded the label or not. Remember, the goal of this algorithm is to make predictions that exceed the label. Right. So it's got to start somewhere. Doesn't really matter where it starts, but let's say that the prediction is going to be 0. Doesn't know anything. We'll predict something. And then what it's going to do is follow it. pretty round. One capital P. I will observe the feature. Remember, I just said that this algorithm was marginally less silly than the one we saw last time. It's not doing anything especially clever, so we're still going to ignore the features. Make it a little bit different. Great algorithm, great card. So let's do that for now. We'll make our prediction. We'll curve the label. Then we'll update. Then our prediction spot up. And kind of equal our prediction today. Plus an increment that's going to be scaled by eta, our learning rate. And you know, we're either going to take a step up. We're going to predict, a little bit higher tomorrow or a little bit less high tomorrow, depending on whether our prediction today exceeded the label. Okay. So we'll add eta. What's the difference between two, our target quantile, and the event that our prediction. If our prediction did exceed the label, then the indicator vector is 1. Okay, so this term is negative 2 minus 2, 0, 1, 2 minus 1 be negative. So if our prediction exceeded the label, we're going to decrease our prediction next time. And if it didn't exceed the label, we'll increase. And one way you can use the algorithm is add its gradient depends on the symbol one. But okay, we've got this like learning rate parameter eta, which sort of you'll see it comes into what the final guarantee is. But you can also think of it as controlling how unreasonable this algorithm is. Okay, unfortunately, like the bound we're going to prove will be quantitatively better the bigger eta is, which is the thing that makes the algorithm less reasonable. Okay. So let's think about maybe like two external things.
Well, we like alternatively. This algorithm is like other alternatives like how the going on
Yeah. So that'll be sort of what this is doing if eta gets big. Doing something a little bit less unreasonable if eta is small. You'll see, when we write down the theorem, and maybe it's obvious that the theorem is better when the algorithm is doing something. Okay, so like let's maybe have that discussion first. Suppose we just wanted to prove a theorem that we've got an algorithm that has really good marginal mean consistency, and we didn't care about it being a reasonable algorithm. In fact, maybe our goal is to make fun of marginal guarantees, and we want to like give an unreasonable algorithm to motivate the conversation we're going to do. Okay, in the spirit of the algorithm we saw last class, which is prediction. Well, you might think, okay, like my goal is just to cover the label 90% of the time. The labels are between 0 and 1. So how about 9 out of 10 times I'm just going to predict 1, which is like dimensionally going to be like bigger than the label, and 1 out of 10 times I'll predict 0, which is definitionally going to be smaller than. Okay, so that'll be really good. Like I'll have perfect marginal mean consistency on multiples of 10. Any rounds with the multiple of 10, I will have done this perfectly. And on all of the other rounds, like I'll be off by at most something on the order of 1 over 2. Okay, so that's a great bound. Similar bound to what we proved for marginal mean consistency, and of course, totally useless algorithm from the point of view of giving us any information at all about the thing we're predicting. It doesn't even look at the thing we're predicting. The only information it's giving us is whether the index, the time index, is a multiple of 10 or not, right? Like totally irrelevant to the prediction. Okay, so like that would prove a really great marginal consistency bound. And so the theorem itself, like our ability to use a good theorem just for a marginal consistency bound gives us no evidence at all of the thing it uses. And by the way, like that's kind of what this is going to do when eta is big, right? When eta is big, what's going to happen is from big numbers to small. Okay. When eta is small, this is like less of a crazy algorithm. It's making small changes, and to the extent that there is a distribution, this will learn that it's the pure distributional quantities and not deviate too far. It'll fluctuate around it. And for this kind of algorithm with small enough eta, you can even prove what are called like adaptive recurrent bounds, which means that even if there's not a fixed distribution, but like there's a distribution that's changing slowly, this thing will correctly track the quantile of that. So for smaller eta more on the order of like 1 over root t, this algorithm is actually doing something. Like it's not cheating, it's doing something that is, it's actually learning some property of the data. Yeah.
Can you say either one of the groups and do like that?
Either one. Generally, if you don't know what the horizon is, you want 1 over root. Either one. Okay, so just for like this algorithm isn't purely ridiculous the way the mean prediction algorithm from last class was. There's a parameterization of it that makes it ridiculous, and in fact, that's the parameterization that's going to give the best theorem. But there's also a parameterization of it that makes it non-trivial. If there is a slowly changing distribution, it'll actually track the correct quantile. Okay. That makes sense. Any prove the theorem, simple theorem that will fail to make that distinction. In fact, it'll just be the theorem that makes the silly version of the algorithm look right. Okay. Here's the theorem. Like the target quantile. And any say parameter eta. This algorithm online marginal quantile predictor, and get into our quantile range. Guaranteed for transcripts. Transcript by satisfying alpha approximate marginal quantile. Alpha the most 1 plus eta over so if we set eta to be something big, like 1, this will give sort of really good, like, statistically implausible rates that will be like on the order of 1 over t. You remember, even if there is a distribution, we're learning from data, we expect our sampling error, like the difference between our in-sample and out-of-sample error to be 1/√. But, you know, if it sounds better than that, that's like a hint that maybe something funny is going on. Okay, but you can also set data to be on the order of 1/√t. Then this gives bounds that are also on the order of 1/√t, and you can prove in that case that there is a distribution. Okay, so this is a range. There are mixed. Alpha between marginal on top of the error alpha. Okay. Got this update rule. Sort of the natural way to write things, you know, like PT, of course, is the thing we have control over. Whether or not the label was below or above our prediction, that's not something that's just something we observe. Nevertheless, like we can solve for different variables, right? We can solve for the indicator variable if we like. And doing so, what we see is that, you know, after all is said and done, after we transcript the indicator of whether at round t the prediction we made was above the label is equal to the difference between q and t plus 1, our prediction at round t, our prediction around t plus 1 minus pt, our prediction around t for a. Solving for a different variable starting from the update. So a funny thing to do, of course, because this is indicator variable of something that we observed or didn't, but like it's totally legitimate because we set plus 1 exactly so that and this is, you know, like the useful thing to solve for, because marginal quantile consistency is exactly asking what is the sum of these indicator ranges. So we can write that down. What is fraction of times the whole transcript that yeah, well, something I'm really for. The first term is just a constant q. Yeah, it's a q, it's still q. And the second term, backed off. Well, second term is this. We're dividing everywhere by t. We're dividing everywhere by eta. It's 1/t times eta. That's the sum for all rounds. Difference between our prediction at round t plus 1 minus our prediction around t. And this thing is a telescoping sum, right? Like almost all of the terms cancel out. All that we're left with is the first term, first prediction on the last prediction. Like the only ones that don't cancel. And so that's just q minus the difference between our final prediction at day capital T plus 1 minus our first prediction at day 1 for eta. And you know, we conveniently arrange things so that our first prediction is 0, so really just q minus our final prediction. Um. Good. So let's just note something about how the update rule works. First of all, remember the labels we're assuming are scaled between 0 and 1. Like almost. And so, if today's prediction was 1 or higher, like we're not enforcing that in the algorithm. The algorithm could set our prediction to be higher than 1. That would be silly. It could set our prediction to be less than 0, even though that would be silly. But if that had happened, like if our prediction was today set to be 1 or higher, then we would definitely cover the label today, which means that tomorrow we would reduce our prediction. Similarly, if today's prediction was set to be 0 or smaller, we would definitely fail to cover the label today, in which case tomorrow's prediction would be higher. And the amount we increase or decrease our prediction is never more than eta, right? Eta times something that's, at most, magnitude of the function. Okay, so what does that tell us about the magnitude of the final prediction? Or would have been the final prediction at one more day? That's what we found that. Yeah, well, we know is that for all t, our prediction never exceeds 1 plus beta. If it exceeded 1, we wouldn't increase it, right? We only increase it by increments beta. The only way it could get bigger than 1 plus beta is if it was bigger than 1 already, and then we increase it. But we wouldn't increase it if it's already bigger than 1. And similarly, it can never go below minus beta, right? Because again, the only way it could get below minus beta is if it was already below 0, and then we decreased it again. But we would not have decreased it if it was already below 0. Okay. And so that means the magnitude of our final prediction, like in the numerator here, is at most 1 plus beta. So if we look at the actual expression for marginal quantile, okay, different. You have to value different. Just all the Q's cancel, all we're left with is the absolute value of our final prediction for A to T, which is at most 1 plus eta for A to T, the bound we have on the max. That's the theorem. It's a very, very simple dynamic algorithm that's sort of based on 1 step history, nudges the prediction up or nudges the prediction down, guarantees marginally at least quantile consistency. And this was sort of like a bespoke analysis that advantage of this convenient identity here, but more generally, you can understand this thing as applying gradient descent on something called loss, why you can also analyze this algorithm in a setting in which there really is a distribution, and at least for small enough eta on the order of root t, prove that it actually learns the correct distribution. Again, marginally, we're so far ignoring it. Does that make sense? Okay. Good. So, okay, now we know, all we need to know about marginal guarantee. setting us up for what will be most of the rest of the class, which is trying to strengthen these guarantees in meaningful ways, these conditional guarantees. But I do want to pause and like use what we've learned first, because there's this sort of major subfield of certain quantification called conformal prediction that is just based on marginal quantile estimate. So now we know everything we need to know to understand conformal prediction. Let me spend time for the rest of the class at least telling you about what conformal prediction is. Okay, good. Let me, we're basically going to apply the things we've learned about quantile estimation, both in the distributional and online adversarial settings, to conformal prediction, both in the distributional and online adversarial settings. Once again, let's start in the distributional setting. I'll follow in by batch. Assume there's some underlying distribution, call it T, for examples. Okay, again, we're not going to have direct access to it. Care about the distribution, but we only have access to it through some sample of data drawn into the distribution. Think about the label space here as being big. So either like it's a multi-label prediction setting, if the labels are discrete. So you've got like an image time classifier that's trying to label images with 1,000 or more different labels, or maybe like real values if we're predicting some numeric thing like going to get or something. But in particular, like what we're going to be talking about are prediction sets, which I'll define in a moment, but they're not going to be so interesting for like binary classification kinds of define them, but this is more interesting for bigger things. Okay, so like what you'll commonly learn applying any like off-the-shelf machine learning technique would be some what I'll call like a point predictor, some model F that takes as input features and predicts for you later. But predicting like a single label might sort of a misleading degree of certainty, especially if, as is often the case, your predictor is not going to have perfect accuracy. It's even like reasonably higher. There's all sorts of things that just are fundamentally noisy processes and predict with perfect error, which is expected. And so the kind of object we want to learn here instead is what's called a prediction set. Instead, our goal will be to learn a function, call it T, mapping features to subsets of them. Okay, so given an unlabeled example X, like a picture taken from the camera and running a self-driving car, we'll produce a set of labels of things that think about the semantics of this as being like things that might be in the end. Ideally, the set would contain only a single example if we were quite confident. Frankly, the thing in front of you is a 6-year-old child. But if we're not confident, we want to know where the uncertainty lies. So we might say, okay, it's either a 6-year-old child or okay. And The thing that we want these prediction sets to satisfy is that they should actually contain the true label with some specified confidence level. If our goal, so given some confidence level, 1 minus delta, our goal is that the probability that on a new example, drawn the underlying, that the true label actually is contained in our prediction sets should be something like 1 minus delta. We want that, if we want 99% confidence, we set delta to be 0.01. We want that 99% of the time our prediction set really does contain the true limit. Okay. Now, again, I'll note that this is not necessarily as strong as we might hope for and eventually ask. Like what we really want, the thing that's too strong, is that we should have 99% coverage on this example. Like conditional on everything we know, we want to cover the right label 99% of the time. We want to know that, given everything we know, if there's not a child in our prediction set, there's less than a 1% chance that there's actually a child in my set. Okay. That is not what I have asked for here, because the probability here is not only over the draw of the label, but also over the draw of the example. This is what the marginal guarantee is. Both. We should note this both as the weakness of the guarantee, but it's also going to be why we can conformal prediction now, given that we've only learned about marginal guarantees. And in some applications, maybe it's enough, but that's certainly what it is. Does that make sense? I'll note also that there's sort of like a trivial solution here, or at least if I turn this into an inequality, if I said I wanted, at least 90% coverage, I could always output the set of all labels. For the label, there wouldn't be very many. So of course, what I really want is I want informative prediction sets that have this property, and like we'll maybe think later in the class about what's the right measure of the informativeness or usefulness for prediction sets, but typically what people do as a proxy for that is they just sort of say, okay, I want small prediction sets. I don't want the prediction sets to contain too many labels. And what's generally done in conformal prediction, not the only way you could do things, but what people generally do in this literature is they prove coverage guarantees as a theorem. They say, under the assumption that examples are drawn IID from some distribution, say, we get 90% coverage, or in the worst case of adversarial example, we get 90% coverage. And then they evaluate the usefulness of the prediction sets for the size inversion. Okay, and it'll become clear, I think, when we see how this works, why that is. But basically, conformal prediction is the sort of, you think of it not as an algorithm, but as like this extremely general like wrapper technique. Like basically, there's going to be this thing called a non-conformity score that I'll introduce in a moment. That can essentially be any function you want. And the guarantees of conformal prediction will hold no matter what function you choose. Ultimately, like the guarantees come from just our ability to correctly estimate the quantiles of that function, no matter what the function is. Okay, so that means that we'll prove that like the theorem we're going to prove is really going to be a theorem not about a single technique, but about a whole family of techniques that can be instantiated by choosing different non-conformity scores. That gives you a lot of freedom in designing exactly what your algorithm does, but of course it also limits what you can prove about it, because like at this level of generality, the theorems you want to prove about the quality of the prediction sets definitely won't be true for all non-conformity scores, which again, we'll see in a moment when we define them, but they're really just arbitrary functions. Of course, to come up with good prediction sets, you probably need to take advantage of some structure of the prediction problem. And what people do is they sort of, for particular prediction problems, try to define good non-conformity scores, typically defined as functions of, like neural networks, for example, trained to exploit structure of the problem. The nice thing is that however you do it, you get these coverage theorems, but typically it leads to, if you're orienting yourself to the literature when you're looking for like a class project, the usefulness of these things to the extent that it's evaluated is evaluated here. Maybe I'll just like hint for those looking for good class projects that maybe that's not the only way you could do things. It might be interesting to do things the other way around. So it's like a high level overview, but like question at that level before we dive a little deeper. Okay. Right. So like the objects we're going to come up with, they're sets of labels, right? So this form of these things, like, y is real values, then it might be that, what a prediction set looks like is, some interval, like from the interval from 0.3 to 0.6, all the prediction is. As we'll see, there's no requirement here that even the real value case our predictions that have interval structure. We could predict an arbitrary set of points, but many natural non-conformity scores will lead to intervals. But right, it's sort of again, we're going to be quite general about what the label space looks like. It doesn't have to be real value. So, like it's just an arbitrary set of labels. So it could also be, the set that contains the labels like the Blueberry Muffin or Chihuahua. I mean, confidence that the thing in the invented either Blueberry Muffin or Chihuahua. Ideally, the prediction set would specify that uncertainty and would say, look, this thing's either a Blueberry Muffin or a Chihuahua. What's the main idea of conformal prediction? So first of all, what's the difficulty? The main difficulty when you sort of see this problem, say, well, the range of my output, my goal is to produce a prediction set. It's really good, right? Like, set of all, so like a k-label problem. There are like 2 to the k different prediction sets. Right, and for every subset of labels of which there are 2 to the k, that could be what I predict my prediction. And for regression problems, for real value problems, alpha 1. So, and so the main idea of conformal prediction, the thing that sort of takes it from this extraordinarily high-dimensional problem and turns it into a simple problem of quantile optimization, is that you're going to use this thing called a non-conformity score to project this like 2 to the k dimensional problem onto a 1-dimensional problem. Okay, that's going to have the effect both of making it a lot easier statistically and computationally, but also of sort of, like throwing away a lot of the possible signal in the problem. And so that's why, like, although what we're going to prove is something about all non-conformity scores. Like, this is really only going to be a useful technique if you find a good non-conformity score that captures relevant structure in the problem. So, a non well, arbitrary constant. Call it F. Takes as input two arguments. Takes as input a feature vector, and it takes as input a label. Now it's a real number. And this could really be anything. Typically, so that these scores like actually capture some signal about the thing you're trying to predict, you would define this score as a function of some machine learning model you've been trained on the data. If you start with some model, you use that to define non-conformity. And maybe like a good intuition, although the meaning of this score will not come up in the theorems you want to prove, but like a good intuition for like maybe what you should be thinking about if you're trying to come up with a good one of these scores. If you have a good model, which predicts things, maybe like what the label is going to be in a regression problem, or the probability of different labels in a classification problem. Like, think of the non-conformity score as representing something like how surprising it would be, given what your model predicts, given the feature, if the label turned out to be one. Okay, maybe like that's the thing you can be like targeting or imagining when you're sort of thinking about what this non-conformity score is, although the theory doesn't care what it is. Again, okay, but think about it as how surprising the given label is to your model. So, for example, you train like a regression model. They will say real values and, have trained a linear regression model today. This is not features that like predictions for what the label is. Okay. Real number. Okay, I don't necessarily trust the model because the linear regression model, and I'm not willing to assume that the world truly is linear, but I've got this thing. Then, like the first non-conformity score you might think of, not necessarily the best one. About way to improve on this naive kind of thing. But like the first thing you might think of is that maybe the score that again should feature X and you realize label Y, so how surprising this label is for the model. Well, maybe it could be something like the absolute value difference between H of X, the prediction of my model, and one. This would sort of be encapsulating. First of all, this definitely like satisfies the brief. There's a function that takes as input like features and labels and outputs the number. And maybe it's, to the extent that the model is any good at making predictions, maybe it's like not a crazy score either. It's saying sort of we're more surprised to the extent that the label is far from the prediction. Now, what is the role of this non-conformity score? Well, the role of this non-conformity score, which because it's outputting a real number, right, is it maps features to this one-dimensional scale, right? Like, what is the non-conformity score? The role of this non-conformity score is to give us a way to parameterize the high-dimensional prediction sets of which there are as many as K to K or all of one, with a single parameter, which is just going to be a threshold on the non-conformity. Okay. So we'll use F are non-conformity core functions. Right. A one-dimensional family of predictions. Or really a one-dimensional family of functions which map features together with one parameter to predict. And what's the function look like? Well, really simple. If I've got some non-conformity score that could be anything, and I want to know what's the prediction set I'm going to assign given feature X. Well, I said it's a one parameter family, so I also need to tell you what that parameter is. Let's call it tau. Given the parameter tau, we're going to map the feature vector X to set of all labels such that if I were to compute the non-conformity score, my function X and feature X and the candidate label Y hat, we're deciding here whether or not it appears in prediction set, map to a value less than it. So given X, I'm going to map to the set of all labels whose non-conformity score when paired with this X is below my threshold. Does that make sense? So for example, like the very simplest running example, this is my regression function. I've got this regression function, and from it, I've defined this very simple non-conformity. Then I would get an extremely simple family of prediction sets that does correspond to center as a prediction. Our regression model that has, like with two steps. Okay, like so this is the generic construction. In general, like the structure of these prediction sets could be complicated, but like this is the non-conformity score, then the structure of the prediction sets is extremely simple. The dimension interval centered as the prediction with width that is just the scaling of this one dimension. So, like the structure of the prediction sets that I get here is fully dependent, really, on what the non-conformity score is. But the nice thing about this parameterization is that no matter what my non-conformity score is, as long as it maps features to the features across labels to finite values, it parameterizes a family of prediction sets that span from sort of, if I make the threshold small enough, sort of prediction sets that have zero coverage. So on the other hand, if I make the threshold big enough, prediction sets that have 100% coverage. If I make the threshold sufficiently large, then my prediction sets will be those trivial ones that always contain the label. And so now there's like, like what this does is it turns this high dimensional problem of finding a prediction set into a one-dimensional problem that is feasible. To find a value of tau that the these prediction sets have, say, 90% coverage, the target coverage level. And because no matter what the non-conformity score was, this tau is parameterizing a family of prediction sets that includes things that definitely have at least 90% coverage. You can get as high coverage as you want. by picking tau to be large enough, the problem's always okay. So what people, what you're going to want to do if you don't want trivial prediction sets is to try to find the smallest value of tau potentially that gets you your target level of coverage. There is always some tau that parameterizes a family of prediction sets that always includes, and that's gonna, yeah, we'll see when we work out the details, but I think you probably already see pretty straightforwardly that coming up with the right value of tau essentially corresponds to computing a 1 minus delta quantile of the one-dimensional distribution of non-conformity. Okay. I want to go through a couple of examples of some other non-conformity scores that show up in the literature to like show you that there's some non-trivial design space here. But then we'll sort of analyze like a basic conformal prediction algorithm, which is really just a quantile estimation problem. And we'll see like the guarantees are entirely agnostic to what the non-conformity score is. Of course, if you come up with a silly non-conformity score, like one that ignores the data, you're going to get silly prediction sets. But you can get good prediction sets to the extent that you've designed a good non-conformity score, which is generally something designed from a good model. Okay. Before we go into that, are there questions at the level of detail yet?
Like, for example, this one never had all of it.
I think the point is that, like, maybe we'll have to think about this a little bit more carefully when we get to the like online adversarial setting. But I think the point is, like, we've got a data distribution. I can always ask the question, what is the distribution on non-conformity scores for X, Y pairs drawn the data distribution? And whatever this distribution is, it's got a quantile. So if I want 1 minus delta coverage, I can define tau to be the 1 minus delta quantile of that distribution. And we'll look at the content of the theorem we proved, but like not so complicated, so you can already probably start working it out. That if that's what we set the threshold to be, we're going to get 1 minus delta. So the fact is that the point is just whatever the score function is, right? Like it maps things on finite numbers. The scale doesn't even really matter. We're interested, so it has some CDF on the underlying distribution, and we're interested in like quantiles of that feature. In the online adversarial setting, we might have to worry about like the function being bounded.
Yeah, we started this at convention, but the fact that it's a non-conformity score, like score that's just like not followed by us.
So, yeah, you're getting actually to a point of terminology that I always mess up. So I think some papers they call it a conformity score. But yeah, like the general thing we want is that like it should be like labels that we feel are sort of objectively less likely should have larger values, and so we're gonna threshold it in labels that have smaller values. The ones with smaller values will be the ones contained in the set. And so I have been calling it a non-conformity score because a bigger number means you don't conform to the expectation. But I've myself been a little bit confused with the terminology, and I might have it where to start. I mean, obviously, you could like build up this theory with everything. Good. Yeah.
I don't know like really anything about conformal prediction, but the setup seems pretty,
The few ways.
yeah. It seems pretty like close or well suited for something like multi-agent RL or something like ActiveCredit. Off the top of your head, do you know if this is sort of been explored or?
Good. So this is again a good source for projects. I believe that there is work using certain quantification techniques, including conformal prediction in RL settings. In RL settings, that distributional setup maybe isn't the best match because you're affecting your environment. There's not like a fixed distribution, but as we'll see, using like the algorithm that we saw at the beginning of this class, you can do all of this stuff without assuming a distribution. I don't know how much it's been developed. I think if you want to pick it up here, you might know more about that. Anyway, I think the short answer is it's a natural thing to do. I think there are some applications, but I think that there's probably a lot more to do, and that's a rich area to explore for your project. Good. Good. So, you know, like basically you need to get your, like, you want to get your hands on a good one. The theorem we're going to prove about coverage holds for anyone. So what is a good non-conformity score? It's one that when you sort of tune the parameter to get the right coverage, actually gives you useful predictions. Now, sometimes some of the literature is sort of kind of like hand design these things, but there's also a literature that takes the natural approach of trying to do backpropagation to train a score that provides like small prediction sets when through this conformal prediction. That's a natural thing to do as well. And when we get to when we get to later in the class, thinking about expanding kinds of guarantees we can get for conformal prediction to give us sort of additional coverage guarantees of various sorts, which will on different structures and features. We'll get to the same kinds of questions, like what are we want our coverage to hold originally on the example lying in different groupings of the data. What are those groupings? Well, again, you can sort of design them by hand if there are some to care about, but there's also the natural question of trying to learn the relevant groupings from data, and there's work on that, including by yeah.
Why do we define T sub S using y hat instead of y?
Okay, because how are we using this? We're like we take as input X. We don't know why. Like Y is the real it. Like we're hoping that Y, when we learn it, will turn out to have been inside this prediction set. Given X, what is our job? Our job is to figure out what labels we're supposed to stuff in the prediction set. What labels are going to stuff in there? Exactly those labels Y hat that have the small non-conformity score given. That makes sense. If we knew Y, we would just put that in.
Currently, how we got conformal score from a different metric. I know we would not want to improve, I guess, but is there a situation where we not want non-conformal score not
Let me first pause the puzzle at what that even means. Then first of all, we need to get input like single X. So like what is a metric? If I think of a metric, normally it takes as input like 2 points. Like what do you even mean by triangle as well? But the short answer is I'm like the theorem we're going to prove is going to put no restrictions on this at all. We're literally going to assume that non-conformity score is like anything. But anything fitting this like type signature. Typically, the design of the non-conformity score, and we'll go through a couple of examples, manifests itself in trying to get these coverage bounds with useful prediction set. But yeah, like it's a function mapping a single point to a number, not. Yeah, so maybe like before we just like prove the generic theorem, just like note maybe that there are other choices for non-conformity theory. Yeah, like suppose we learned a regression model, a regression model, or something more complicated like a gradient boosted regression tree or whatever. Maybe it's even like a pretty good model. and we use the simple non-conformity. Maybe our model is pretty good, so maybe to get 90% coverage, we don't need to take this out and be very big. We produce very good stuff. Like still, this isn't gonna give us like a super satisfying kind of uncertainty quantification. If anyone like give me a reason why might want to stay more sophisticated on this sort of that. Like what are the what the properties of these prediction sets are gonna have if I use this concept? Yeah.
Yes, there's side.
Yeah, but like if I use this non-conformity, or what I'm gonna get are prediction intervals centered at the prediction the point prediction of the model that have width 2 tau, no matter what x is. Right, like we're just sort of saying, okay, you know, like on average over this model, you should sort of think about the predictions of the model as being only correct up to plus or minus 2 tau or plus minus tau. But we're just going to say that uniformly over everything. Okay, so like it's true that like there's some tau for which intervals of width 2 tau will have the correct coverage on average, but it might be that the model is substantially more confident, substantially more accurate on some points than others, and the kinds of prediction sets that come out of using conformal prediction with this particular non-conformity score are just going to be structurally unable to reflect that kind of variation and just have uniform with definitional no matter where they are, because you know there's only a single parameter and the way we define the non-conformity score doesn't vary the width depending on where. Okay. So you might say, okay, well, you know, that's because we're only asking for marginal guarantees, like that's what marginal guarantees have. But that's not quite right. So, like, I don't want to undersell, but like I'm going to spend a lot of this class asking for stronger guarantees, but I don't want to undersell conformal prediction. Like a lot of conformal prediction has stuck in this sort of marginal guarantee framework, and nevertheless done things that are substantially more useful than this. And that generally comes from just trying to design a clever number. So for example, like one thing I could do is if I'm training a linear regression model, use a linear regression model, something that minimizes squared error. You know, like what it's trying to do is it's trying to approximate the mean of the label distribution for each point. It's spread them enough to be different, right? It's how the squared error is minimized at the mean. But that's like fundamentally the wrong problem for coming up with a prediction interval, which is really a question of quantile, right? Like if I want 90% coverage, what I want to do is I want to express, you know, the middle 90% of the distribution, cutting off the 5% tail on either end. And so learning the mean, trying to learn the mean of that label distribution is just fundamentally the wrong path. Okay, but maybe it was, but like that was all you gave me, and I can't change it. I just have to come up with a non-conformity score. Maybe this is like a reasonable thing to do. But if I can design a non-conformity score, including the model that I trained, maybe I could have tried to predict quantiles directly. Okay, so I could have done that. So that's a popular non-conformity score that when you use this technique in the literature, it's called conformalized quantile regression. But the point is, don't learn a predictor aiming to predict the mean of the label distribution. Learn one predictor or maybe two predictors aiming to predict the quantiles of the label distribution. Okay, so yeah, we instead pick different non-conformity score as follows: formalize quantile regression. We can find a non-conformity score as follows. We could train two quantile regression models. For quantile regression, That's minimize pinball loss when you're training your model rather than minimize square loss. Remember, pinball loss is minimized at the target quantile of this the distribution that says square loss is minimized at the mean of the distribution. We train two quantile regression models, say H delta 2 and H1 minus delta over 2. Students predict delta over 2 and 1 minus delta over 2 quantiles. Effectively. Okay. And then, if I've done that, I can define the following non-conformity score. Again, non-conformity score is just a function mapping this type signature. Otherwise, it's be whatever we like. So it's going to take as input feature, vector, and a proposed label. And what's the number it's going to output? Well, just whatever's bigger. But we're going to evaluate both of our quantile regression models. The one aiming to predict the delta over 2 quantile, and the one aiming to predict the 1 minus delta over 2 quantile on X. And we'll take whichever's bigger, the difference between the predicted delta over 2 quantile of X and Y, and Y and one minus delta. Predicted 1 minus delta over 2 quantile. What's going to happen here when we try to produce prediction sets using this non-conformity? I think the like the way you should think about it, a useful way to think about it is, I think a useful rule of thumb when you're thinking about and designing non-conformity score measures is what would have been the correct thing to do had the models you were basing your non-conformity scores on actually been correct? Like, what if they were truly predicting the distributional quantity? How should you then construct your prediction interval? And then, since we don't want, we want worst case coverage, we don't want to assume anything is correct. Think about modifying the prediction set starting from what would have been correct had your modeling been correct, and then fixing it. Okay, so what's happening here? Like, we've trained these quantile regression models that supposedly predict the delta over 2 quantile and the 1 minus delta over 2 quantile of the label distribution. So, like if we were right, the ideal prediction interval would be, for prediction, for predictions about the quantiles were correct. With this, the interval, the centered interval that's got 1 minus delta coverage would have its left endpoint be at the delta over 2 quantile of the label distribution, and its right endpoint be at the 1 minus delta over 2. That would be the interval we would produce. And then, like, what is how is the non-conformity score defined? Well, it means that if we produce this interval, and then the realized label falls outside of the interval, the non-conformity score will be the distance between the label and the interval. Similarly, if the realized interval falls inside of the interval, the non-conformity score will be the negative of the distance of this point to the nearest end. The non-conformity score here can either be positive or negative. Positive if the idealized prediction interval that just treats the predicted quantiles as if they were correct, does not contain the label. And negative if it does. Okay, and then what's the, like what does the conformal prediction do to these idealized prediction intervals? Well, if we define the non-conformity score in this way, then the prediction interval we're going to get, given x, is just, well, the left endpoint will be our prediction for the delta over 2 quantile of x minus tau. And our right endpoint will be our prediction for the 1 minus delta over 2 quantile of x plus n. Okay, so tau will serve to uniformly expand or contract prediction intervals that should have been correct if only our quantile regression model were correct. Okay, so if our problem had structure that was correctly modeled using our family of quantile regression models, and we succeeded in optimizing control loss. So if there was structure in the problem, and we succeeded in optimizing, and we came up with really good quantile regression models, then what we would find is that, the 98th percentile quantile of this non-conformity score would be 0. We would just, tau would be 0. We would just use the original prediction intervals, like we cover the original prediction intervals that we should have used had the model been correct, if indeed the models were correct. And if they weren't correct, if they were sort of systematically off in that using these prediction intervals didn't have 90% coverage and instead had 80% coverage or 95% coverage, what this will do is it will uniformly expand or contract the intervals again. 90%. And so again, like here, tau is still just a single parameter, right? So the degree to which we expand or contract these intervals is constant over all examples. But our non-conformity score is defined in terms of the quantile regression models, which themselves might be picking up on all sorts of structure and making very different predictions for different examples. And so the intervals themselves are not of uniform length. To the extent that there's actually structure, to the extent that sort of the quantiles, the visuals of our model or whatever, vary across examples, our prediction intervals will similarly vary in width across the examples. Okay, so this at least has the potential to produce informative quantification of uncertainty, although, the realization of that potential will, of course, depend on our ability to learn good quantile regression. And again, we haven't proven it yet, but the coverage guarantees of these prediction intervals will not depend on any assumptions like that. The coverage guarantees will always be worst case because we can always get correct coverage by picking the right value of tau, and that turns out to be a marginal quantile estimation problem, which we've now seen is a pretty easy problem to solve, both in the online adversarial and the batch setting. But like here, we're seeing an example of a non-conformity score that at least has the potential to be informative. In fact, to the extent that we have machine learning models that might, without any theoretical guarantees, nevertheless sometimes pick up on useful structure about label quantile distributions, we get to take advantage of it, right? Like to the extent that we get it right, we won't modify them at all.
Yeah, so for this, I guess the other concept we talked about seems like you're kind of assuming the error is sort of semantics about whatever grade anything like this. But I imagine you could do a similar thing with your data was like squished at the bottom and just take one of the margin quality others.
That's right. Yeah, the only thing is not like, again, you've got some complete design freedom.
Yeah.
To determine them to be some arbitrary function. So if you didn't like the errors were symmetric, you could make them non-symmetric. And as we go on and start talking about, the only important thing here is that the family of prediction sets be parameterized by like a number, a single number. That's what's going to make it a quantile estimation. Although as we go on in the course, talk about estimating quantiles with additional guarantees, we're going to expand this parameterization to make tau a function that will give us more freedom in varying what we do across the data.
So, given that we have this slide, is there, like, say you wanted to, or I guess I'm typing that, over the course of this special, is there a way to learn good shape? Or do you have to kind of assume one and try it out? And then like another one, try it out.
Okay, so I guess when you say the shape of the uncertainty set, it really like any kind of geometry here, once we parameterize things this way, is that it was a non-conforming work. And so there is work that tries to in automated ways, but like once you set out a goal, like you want to minimize the size of the prediction set subject to how being an 90th percentile quantile is not. This is the kind of thing you can start trying to optimize. So there is work, again, I don't know how extensive it is, and I'm sure there's latitude here for interesting projects, but there is work that attempts to approximate all of these quantities with differentiable functions and apply stochastic gradient descent. Okay, I mean, like you've got to do, but like it's not immediately a differential optimization problem because it's like a hard constraint whether it's hard cutoff, whether the label is set or not, just the size of the prediction set, it's not a differential function of anything, but to the extent that you can approximate those things with differential functions, you can apply the normal sort of optimization of machine learning pipeline to try to optimize for that. And at least some people have tried to do it. There's no reason you can't. There's no reason you can't change the design of the non-conformity for a optimization problem, where the constraint is that the tau is a 90th percentile quantile of the score you design. And the thing you're trying to optimize for is the size of the prediction set given time.
This I require try a certain shape or something and then somehow create it or there's something like over the course of the sequel.
Well, there's probably many ways you can do that, but like in some generality, like but let's say it's a regression. So, and let's say the features are real values. So S, if it's these real value features, then one real value thing. So S is some function from d plus one numbers to one number. You could parameterize that with a neural network. Okay, so now S is a differentiable function. There's some mapping, given tau, there's some mapping that S induces from features to size. That's not different. You're going to need to, if you want things to be differentiable and be able to pick gradients, you're going to need to approximate that with some differentiable function. So you could go through that exercise. And now, in principle, you've got, a differentiable objective where what you care about is the average size of the prediction sets, and then you can try to, cover into the constraints, and you can try to optimize it. Again, I don't know, I think there's some work in this line, I don't know how extensive it's been, I'm sure there's room for more. But that is the kind of thing you could. Imagine doing. I mean, if your quantile regression models were perfect, and we're able to learn the true conditional quantile given features, but probably they won't be. Learning in the first class that it is, so that we will talk about the version of the learning true conditional distributional properties is not possible. And so, like it's saying, look, if your model is really good already, we'll set tau to be zero. But we're giving ourselves freedom to set tau so that we can run the split conformal method, which we'll see at the beginning of next class. That will promise that no matter what your model is, even if it's wasn't that great, you'll always get 90% coverage, and you can try to optimize for the size of your sets by learning better. So basically, like, when can you provably learn good additional quantile predictors? Well, only under sort of strong assumptions about the world, like you can, like for example, if I assume the world is linear, linear regression is really good, but otherwise not necessarily. Sort of one part of the goal here is to be able to take advantage of good models when they happen to be good, without having guarantees like coverage depend on hard to verify them. Well, if it was good, if it was perfect, tau would be zero, right? If it wasn't, your original predictor probably didn't have conditional guarantees, then you're just gonna get coverage by forming this sort of relatively simple expansion. And again, this is not one example of a non-conformity, there are plenty of others. So we're out of time now. My plan for the beginning of next lecture, I'll just sort of wave in front of you one more non-conformity score, one that's popular for classification problems. We haven't seen one of those yet. Again, the philosophy is sort of, because you've got a model that sort of looks like it's predicting class probability for different labels in the future. Let's produce the prediction set that would be the right thing to do if only those probabilities were correct. And then let's conformalize it. So let's expand or subtract it essentially to correct for the possibility that it might be your audience. Okay, we'll just see some examples of interesting non-conformity scores, and hopefully then if you are so inclined, go out to your own problems and think about what a good non-conformity score might look like. And then we'll give the sort of generic black box wrapper, which is called split conformal prediction, that lets you take any non-conformity score and turn it into a way of producing prediction sets that have the criteria. Okay, I'll keep that up.
Like data set.